Hello, it's Mr. Claudia here, and today we are learning about equivalent resistance. Now, this is the last section on circuit analysis in this course, which is good because we've built on last week's tough lesson, and now we have something to add to it, which is this equivalent resistance concept. So I'll let you go through the slides yourself. I mean, essentially, I think this is written in the slide, but equivalent resistance means that if I take this circuit, I can actually, for a series circuit, I can replace these three resistors in series. I guess I haven't mentioned, resistors could just be thought of as lamps, right? They're light bulbs, right? The resistor is something we use when we're making a circuit, but you can think of them as light bulbs if you want. The amount of resistance that each of them causes, we can add that all up and replace them. So I can replace this, and you have this in your notes, but I'm going to replace this with an equivalent resistance. And how do I know what the number is? Well, if they're in series, I just add them all up. So 10, 15, 18 ohms. Things get a little more difficult when I'm dealing with a parallel circuit. To find the equivalent resistance, again, the equivalent resistance is this. The one resistor that replaces these. Well, I have to use this formula. 1 over our equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. And there's no real shortcut to solving this. It's annoying math each time. So I have 1 over 10 plus 1 over 2 plus 1 over 1. You could solve this using adding up your fractions. You could just go right to your calculator. So this is 1 over R equivalent. So I have 1 divided by 10 plus 1 divided by 2 plus 1 divided by 2 plus 1 divided by 1. Now make sure you're comfortable with your calculator and you do a few of these to practice. I know that mine can do basic order of operations, so it's going to add up these numbers correctly. So I get 1 over R equivalent is equal to 1.6. Now you could cross multiply, so you're going to get 1.6 R equivalent is equal to, I'm going to cross multiply, so that's 1. And so then I get R equivalent is equal to 1 divided by 1.6, which is 0.625 ohms. I'll show you this again, but a quick way to, once you get to 1.6, you could just, to this answer, and you know it's 1 over R equivalent, well, you could just take the inverse of both sides. So I get then R equivalent is equal to 1 over 1.6. I could just say 1 divided by answer right away. Okay. Sometimes you have a button to do that too, but I can't find mine, or maybe I don't have it. Okay, and notice the difference between these two questions. When we look at series circuits, all of those resistances add up, so we get a big resistance. When you look at parallel circuits, the equivalent resistance is smaller than every resistance on its own. And that's an important note to make. This is a good example in your house as you continue to plug in all of your things that you plug into your outlet in your wall. They're all connected in parallel. So you can keep connecting circuits, keep connecting circuits. The resistance goes down and down. If you think about V equals IR, as your resistance goes down, your current goes up. So this could cause you to have too much current in your lines, and then you blow a circuit breaker, or your lines go on fire. So equivalent resistance is interesting because as you have more and more, the resistance goes down. Okay, so let's start applying these with a bunch of examples. I want to replace this with an equivalent resistance. Again, if you just want to get an idea of what I'm doing, I'm going to replace all of this with something. So what is that R equivalent? Well, because this is in parallel, I have to use that formula. 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Okay, so then we don't do any funny business or shortcuts. It's still 1 over R equivalent. This is 1 over 10 plus 1 over 20 plus 1 over 30 plus 1 over 40. Now, to ensure you don't make any mistakes, it often is a good idea to look at each of these individually. Like 1 divided by 10, that's 0.1. 1 divided by 20 is 0.05. 1 divided by 30 is 0.0333. And 1 divided by 40 is 0.025. So now I add all those things up. And I get 1 over R equivalent is equal to 0.20833. Remember, that's not my final answer. My final answer is 1 over that number. So I have 1 divided by answer. Oops. Okay, 1 divided by 0.20833. And I get about 4.8 ohms. Okay. So that's equivalent circuit. And you might be thinking, well, why are we even bothering to do this? What's the point? Well, now, if I know that this is 24 volts, and I know that this is 4.8 ohms, then I can figure out the current, the total current in the circuit. Once I know the total current, I can start to figure out how much current goes into each of these different legs. So it's kind of to help me build a final solution. Okay, let's do a more difficult equivalent resistance. Okay, now if you look at this question, it's a combination of series and parallel circuits, so I can't just use one of the rules. First of all, let's label everything. So let's call this R1, let's call this R2, R3, R4, and R5. Okay, so what we have to do here is start at the furthest edge and work our way back. Unfortunately, we have to do this step by step. So I'm going to replace these two resistors with an equivalent resistance. Now, because they are in series with each other, I just need to add the two of them together. The replacement I'm going to call R45, and that's going to be 1 ohm plus 10 ohms gives me 11 ohms. So now I'm going to redraw the circuit. So I have my voltage source here, plus minus, and then I have, okay, so I have a resistor here. I have a resistor here. This was 1, this was 12. I have a resistor here, which is 4. And now I have this, I've replaced this with the resistance like this. That's worth 11. Okay, well now when you look at this again, we're working our way from the outside in. I know that these three are in parallel. This is not really part of this, right? It's not really in parallel. It's going to be in series with these three, but these three are definitely in parallel. So I could find the equivalent resistance. Again, 1 over, I'll call this R2, 3, 4, 5 is equal to 1 over 12 plus 1 over 4 plus 1 over 11. Don't get too caught up in this conventions of naming. Worry more about getting the correct answer and keeping your diagrams clear. So now I have 1 divided by 12 plus 1 divided by 4 plus 1 divided by 11. And that gives me 0.4242. So then to find R2, 3, 4, 5, I have to find 1 over that number, 1 divided by answer, and I get 2.357 ohms. Does that make sense? Yeah, it should be a number that's smaller than each of these numbers. So now when I draw my circuit, it has this voltage source, plus minus. It has a resistor of 1, and then it has this resistance of 2.357. Well, now we're almost there. You can see that this is clearly a series circuit. So the R equivalent, the total R equivalent is 1 plus 2.357, so I get 3.357 ohms. Isn't that neat? Isn't that frustrating how much work it is? So now you've got an idea of how equivalent resistance works. Let's look at some of our toughest questions, which is how to analyze a circuit like this. Look at that word, solve the following circuit. Solve means I want you to tell me everything. I want you to tell me all the voltages. I want you to tell me all the resistances. I want you to tell me all the currents. So last week what you would have done is just try to use Kirchhoff's law. Let's look. Let's see if we can solve it. Well, I know the voltage here is 95. So remember, we talked about voltage is money. So $95. But then I don't know any other voltages. So I can't use Kirchhoff's voltage law. What about current? Well, I don't know any currents. So what I really need to do is figure out what the equivalent resistance is, then use that to figure out my current, and then work backwards. So in this case, and we'll talk about strategy more, I have to find an equivalent circuit. And that's not going to be easy, because look at all these things. We have lots of parallels and series. We start from the outside in. Let's first simplify this. Now these two are clearly in series, so I'm just going to add up the two resistances. So let's redraw the circuit. And we go up, and I have a 25 ohm resistance here, and then we have a 10 ohm resistance here, and when I add these two up, when I add these two up, I have 5 plus 15, so it becomes 20. I want to show our steps there. R34 is equal to R3 plus R4, which is equal to 5 plus 15, which gives you the 20 ohms. Okay, so now we're a step closer. Now I have these two resistors. They're in parallel with each other. So I have to use my my parallel rule for equivalent resistance. Let me redraw this circuit. Oop, that was a bad resistor, but that's 25. We know we're going to replace these with some amount, and it's going to look like this. Okay, now I have to do that difficult math. So it's 1 over R234 is equal to, what do we have? 1 over 10 plus 1 over 20. 1 divided by 10 plus 1 divided by 20. That gives me 0.15. And then we go R234 is 1 over that, 1 divided by answer, which is 6.667. Okay, ohms. So this is 6.667. Okay, great. And now we're almost done. We just need to combine these two to an equivalent resistor. So let's go and redraw this one final time. I have and my R equivalent is equal to 25 plus 6.667, which gives me 31.667 ohms. And we know this is 95 volts, right? That's what we were told. Okay, so now we've done all this work to figure out our equivalent resistance. What was the point? Well, the point is, now I know I can figure out the current, because I know VT or V naught, whatever you want to call it, and R equivalent. So I know that using Ohm's law, remember if I know two things, I can find everything. So VT is equal to I T R equivalent. 95 is equal to IT 31.667. So I take 95 divided by that answer, and I get IT is equal to 3 amps. So now, if we want to go back to the original circuit, I know that coming out of here, I have 3 amps. Going through here, I have 3 amps. Then I go into this point with 3 amps. It splits up somehow, and then again at the end, I have 3 amps. So I'm not really sure what happens in here. I know it splits up somehow. I don't know how much goes this way, and I don't know how much goes this way, but I'll figure it out. But I do know this one. I can figure it out, right? So V1 is equal to I1R1. We know that the current here is 3. Sorry. This is 3. And the resistance is 25. So this is equal to 75 volts. So I know I can't really go any further with my current, but I can go further with my resistance, or sorry, with my voltage. If you remember, with voltage and now using the voltage law, I can make different loops. So if I leave here at $95, I now know that this is 75. I just figured that out. So I leave home $95, I spend 75, then I spend if I go this way, if you look at this one loop, I would spend my remainder here. So actually I can figure out what that is. Let's draw the loop. So I know Vt is equal to V1 plus V2. And so that is 95 is equal to 75 plus V2, and then I get V2 is equal to 20 volts. Now if I know that this is 20 volts here, and I know the resistance, I can find the current. If it's getting confusing, that's okay. We could make a table maybe, because it is getting hard to keep track of everything that we know. We know that there are how many resistors? 4 resistors here. So I'm going to make a little table. Remember I have V, I, and R. So I have my first, second, third, fourth resistor, and then total, or the T is what we usually use to show what's happening over the battery, right, or the source. So let's put in, because we know quite a bit of things now. So R1 was 25, R2 was 10, R3 was 5, R4 was 15. Our equivalent resistance, or our resistance over the whole thing, was 31.667. Our V1 we just found is 75. Our V2 we just found out was 20. Our total was 95. And our currents, we know that this number 1 had 3 amps, and the total had 3 amps. This now resembles really a question from last week. I just found out the voltage, so it's easy for me to figure out what the current is here. V2 is equal to I2R2. 20 is equal to I2 times 10. So I2 is equal to 2 amps. So now we know that there's 2 going this way. You can see that this is just about been blown open. If 2 amps are going this way, then I know 1 amp is going this way. By KCL, I1 is equal to I2 plus I3. So the current coming in, 3, is equal to the current coming out, which is 2 plus I3. So I3 has to be 1 amp. So this has to be 1 amp traveling through, but actually it's also the same because these are in series. The 1 amp is the same in both of these resistors. So I can fill this in. This is 1 and this is 1. And now you can use Ohm's law. V3 is equal to I3, R3 is equal to 1 times 5 is equal to 5 volts. And V4 is equal to I4, R4, which is equal to 15 volts. Whew, there we have it. We have solved this entire circuit, a long process. We had to find equivalent resistance, go down to the most basic, solve for current here, and then we worked our way backwards. There's an important slide at the end of this of your presentation there. How do I know whether to use KCL, KVL, or equivalent resistance? Well, if I give you a voltage of the source and only resistances, then you should use equivalent resistance. That was like a question we just did. If I give you a mix, so if I give you some resistances, some voltage, some currents, you probably don't need to use equivalent resistance. You probably use your KCL, KVL, kind of like last week's questions, and Ohm's law, I guess. So this is probably a harder question, which we'll see. You have some homework problems to work through this week, and good luck with your circuit analysis. Until next time.